Okay, good morning again. This is Professor David J. Delos Reyes. It's August 19, 2023. The time is around 3:21 a.m. It's Saturday morning already. Okay, since it's Saturday morning and we've been saturated with long video lectures for the whole week, okay, my discussion for alternating current circuit will just be, I will just give you the final summary of Thevenin's theorem and Norton's theorem. Oh, this is for life because this will now be the summary. Okay, so this will now be alternating current circuit, lesson number 23, the summary of the Thevenin's and Norton's theorem concepts. Okay, so you will not forget the concept on how to compute for the load current, okay, of a ZL connected across the active network. Okay, let's proceed. Okay, we passed by already from the lessons on Thevenin's and Norton's theorem. Even the examples, I give you individual examples for the Thevenin's and Norton's. And actually what comes out on the IL was the same for both the Thevenin's and Norton's. And for this morning, I will now just give you the plain summary of the concept so you will not forget. Because after this, we will be having another solution of circuitry, advanced solution of circuitry, that is the so-called superposition theorem. Okay, let's proceed. Alternating current circuit, lesson number 23. The title of the subject matter for this morning will be Summary of the Thevenin's and Norton's theorem. I will just give you a brief summary. I will discuss how the concept works and how to compute for the current for both theorems. Okay, let's proceed. For the Thevenin's theorem is referred to as the so-called constant voltage source. So under the study of circuitry, constant voltage source, meaning it's the Thevenin's theorem. Okay, that's the name given to Thevenin's theorem, constant voltage source. Okay, let's try to bring out the figure. This is an active network. Active network contains impedances and voltage sources of EMF. It could generate its own power. So there's a power source inside. Okay, and across the terminals of that active network, okay, of course there will be line number 1 and line number 2. And if we try to connect a load impedance, the problem is just asking what will be the load current, okay, passing through DCL if it is connected to that given active network, which contains, okay, voltage sources and sources of MF and some impedances, because it's an alternating current circuit. Okay, let's try to bring out the procedure on how to take the equivalent, Thevenin's equivalent of this active network, okay, the one inside. Number 1, solve for capital letter E with the subscript TH, meaning Thevenin's open circuit voltage E. So ATH is referred to as the open circuit voltage. If we try to disconnect the load, and you will get your voltmeter, then measure the resistance. It's open already, right? If you try to measure the voltage here by using a voltmeter, that is referred to as ATH. And theoretically computing for it, that will be a problem for us engineers, right? Use your knowledge of Ohm's law and how to compute for this one. Okay? But by using the multi-tester, you just stop it here, and what comes out, that will be termed to as ATH, the Thevenin's open circuit voltage. Okay? Number 2, solve for capital letter C with the subscript TH. TH refers to Thevenin's. Capital letter C is impedance, meaning the equivalent of CTH is the so-called open circuit impedance. Upon the disconnection of the load, if you will get your impedance meter, you tap it here. Okay? Impedance meter. It is not just only the resistance meter or the capacitance meter. It's an impedance meter. It could measure the vectorial sum of a real part and imaginary part. That's why it's so-called impedance meter. You tap it here, okay, and you could measure the magnitude of the impedance. Okay, that will be CTH. Of course, the condition, the circuit should be open, right? Right? This is open. You tap your impedance meter here, what comes out will be CTH. It is the open circuit impedance. Number 3, draw the Thevenin's equivalent, okay? Just draw the Thevenin's equivalent. And this is very important. The Thevenin's equivalent, the figure will be something like this. We got an alternating current source. In series with it is CTH. Then try to reconnect the load. So for a Thevenin's theorem, the constant voltage source is connected with the open circuit impedance. Okay? That's the nature of the Thevenin's theorem. The open circuit voltage should be connected in series with the open circuit impedance CTH. And the load is connected again. So as we could see it, right? The resulting configuration will be a series circuit, meaning the CTH is connected in series with CL and connected, of course, with the open circuit voltage. So this is just a simple circuit now, right? We got two impedances in series. So to take the total impedance, we take the vectorial sum, okay, and to compute for the circulating current, it will be the applied voltage by this divided by the vectorial sum of CTH plus CL. That's why for step number 4, solve for I sub L. And the formula on how to take the value of I sub L, considering a Thevenin's theorem circuit, it will be ETH, the open circuit voltage, all over the vectorial sum of CTH plus CL. Okay? For Thevenin's theorem, the connection should be series. Okay, that's the nature of Thevenin's theorem. And the unit of this current here is amperes, and this is a vector current, meaning it has a magnitude in an angle of inclination. Okay. For Norton's theorem, the other name for the Norton's theorem is the so-called constant current source. If Thevenin's is constant voltage source, Norton's theorem is actually constant current source. If we try to bring out the figure, it's the same as on the Thevenin's. We got in an active network connected across its terminals, it's a load CL. And the problem is just asking what will be the load current passing through it, considering for the meantime Norton's theorem. Okay, procedure number 1. Solve for capital letter I with the subscript SC. SC is short circuit and capital letter I is current. Okay, the meaning of I with the subscript SC is actually short circuit current. Short circuit current. You try to disconnect the load, right? You try to disconnect the load. Then connect an ammeter across it, an ammeter. Disconnect the load, you short the terminal, but connect in series an ammeter. Okay? And take the reading. And that reading is termed to as I short circuit. Okay? So you see now the difference for Thevenin's and Norton's. For Thevenin's, what you will do is take the voltage reading over here, voltage reading. So you will place a voltmeter over here, right? Voltmeter. That's why it is a constant voltage source. Across the terminals, connect across it a voltmeter, so you will get ETH. For a Norton's, you short the terminal, but connect in series with it an ammeter and take the reading of the ammeter. And the reading of the ammeter is termed to as I with the subscript EC, meaning short circuit current. Okay? Number 2, solve for C sub n. C sub n is a capital letter Z with the subscript n refers to Nortons, and capital letter Z is impedance. How do we get Cn? It's the same as in the Thevenins, okay? You remove the short, okay? You get an impedance meter, connect it across the terminal, impedance meter. So take the reading of the impedance meter. Of course, the unit will be ohms, right? And that is referred to as the so-called C sub n. That is the open circuit impedance. Actually, the open circuit impedance for Nortons is the same as the open circuit impedance for a Thevenins. The procedure on how to compute it theoretically are the same. Okay? So at least you now know the difference. For number 1 under Thevenins, it is just the open circuit voltage that you will be computing. For the Norton's theorem, number 1 step is the short circuit current. That's why it is the constant current source, and this one is the constant voltage source. Number 3, draw the Norton's equivalent. Okay, after computing for I short circuit and Norton's impedance, draw the Norton's equivalent. And the Norton's equivalent is this one. This is the voltage source, okay? And that voltage source should be connected in parallel with C sub n. And D sub n, C sub n, then we try to reconnect the load again, right? So, when the load is disconnected, okay, the constant current source is connected in parallel with the Norton's impedance. Okay, you see the difference? Under Thevenins, they are in series, right? But under Norton's, they are in parallel. The constant current source is in parallel with the Norton's impedance. Then try to reconnect the load. So what comes out? This is C sub L, right? Connected now in parallel with C sub N. And the problem is just asking for I sub L. Because I short circuit is already given. We know C sub N. C sub L is given, right? So the only one unknown is the load current IN, right? So from this circuit, we know the short circuit current source from step number 1. We know C sub N from step number 2. Then we drew the Norton's equivalent. The total current coming from the constant current source is I short circuit. Okay, the current passing through the load is IL. So if this is I short circuit, what is going into the impedance, Norton's impedance, will be the difference of I short circuit minus I sub L. So the current entering here is I short circuit minus I sub L. And by using the voltage, across C sub N is actually the current passing through it times C sub N. And the voltage across C sub L will be the current passing through I sub L, C sub L times C sub L. Okay, that's how we derive this one. Then we try to indicate the value of the current passing through C sub N as the difference of the short circuit current, the computed from step number 1, minus I sub L. So this is I short circuit minus I sub L. The current passing through this times C sub N is actually the voltage across this. And this should be equal to the voltage across this because they are in parallel, right? Right? This is I sub L times I sub L. And if we try to simplify this one, I short circuit Cn, I sub L Cn equal to I L Cn. We put this on the right, then we try to rearrange. Okay. There will be a common factor I sub L. This is I sub L common factor times the quantity Cn plus Cl close quantity equal to this one. We put it on the right. I short circuit times Cn. And solving for I sub L now will be I short circuit times Cn. Okay, we divide both sides by Cn plus Cl, so it will now be over Cn plus Cl, and the unit is amperes. Okay. So for a Norton's theorem, this is the formula on how to take the value of IL. And for a Thevenin's theorem, this is the formula on how to take the value of isobel. This ETH is the constant voltage source. That's why it is a constant voltage source if it's Thevenin's. Okay? And under Norton's theorem, this IEC is the constant current source. That's why Norton's theorem is referred to as the so-called constant current source. Okay, that's it, guys. That's the summary of the Thevenin's in Norton's theorem. For as long as we live, this concept will not change. Okay? So for those of you who are studying electrical engineering or just watching concept from electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJDelosReyes. If you want to share it, please click share. I am assuring you, try to watch my long video format discussion on alternating current circuit. You will learn something from it. Okay, good morning from Los Angeles. Professor David J. De Los Reyes.